unpainful as possible. All right, so this is chapter 9. Maybe. Chapter 9, hypothesis testing for a single population. This is where we're applying. The last several chapters, have you felt how they've kind of built on each other? This is more of the same concepts, okay? So what's most important is that hopefully you're starting to grasp or feel a little bit of a deeper understanding into like normal distributions and kind of how they work and how the z-scores are always consistent, right? Because they're put into those units of standard deviations. So whenever we're looking for 95%, it's always a z-score of 1.96, right? Things like that. I'm not asking you or don't expect for you to be experts at this stage, but I am hoping that you're starting to kind of see some of the patterns. If we had, another year to work on this, you would become very comfortable with it. But it's not really necessary. It's kind of like Damien said. I'm planning to be an accountant. I don't know that I need to know all this. And you probably don't need to know all the specifics, but the concept is valuable, okay? All right, so hypothesis testing. What's a hypothesis? What is it? So an educated guess, right? In science, the way we use hypotheses is you make an educated guess about something, often based upon what you already know, right? And then you test it. So in statistics, it means the same thing, okay? In fact, they use statistics to test things in science, right? In fact, the reason you guys are in this class right now instead of in Mr. Stinchcomb's general statistics class is because the business industry recognizes that business owners, even though it's the same math, use it slightly differently. And social sciences use it slightly differently. And the harder sciences use it slightly differently. And so there's this move toward having statistics classes that are geared toward each discipline separately. Same math. You're not going to learn anything different, really. So for hypothesis testing, we're going to talk about 3 different ways or 3 different types. First, we want to test a population mean. So again, this has to do with us taking a sample from the mean and then asking ourselves what the population mean is based on the sample information. Okay? So again, this is what we've already been doing the last couple chapters. But now we're going to ask ourselves, from what I know from the sample, what's the likelihood that the population mean is a certain amount? Okay? And they further break it down to where you know the sigma, right, which is the population standard deviation, or if you don't know it. And as you'd probably guess, this uses the z-score, and this uses the t, right, the student t distribution. And then population proportions too. That's where it's broken as a percentage, right? 63% of the population. Remember that whole thing? We've done that in the last 3 chapters again. So I took a sample and 23 out of the 60 exhibited some characteristic. What's the likelihood that the population exhibits the same characteristic? That's what we're doing with this, okay? All right, so here's some terminology they want you to understand. A hypothesis is an assumption about a population parameter, such as the mean or a proportion. So our hypothesis is that educated guess about the population's mean or proportion. So there's some examples they give you. The mean data use for smartphone users is 1.8 gigabytes per month. That would be a hypothesis, right? Population proportion, the proportion of cell phone users with 4G contracts is 62%. Again, that'd be based on something that would lead them to make that hypothesis. And so the whole point of this chapter is testing these hypotheses. Okay, if you think that the mean data use for smartphone users is 1.8, let's devise a test to see if it is, right? Every hypothesis test has what's called a null hypothesis and an alternative hypothesis. A null hypothesis is always represented as H0, and it represents the status quo, or things as they are right now. It's always stated as a belief that the population parameter is either less than or equal to something, or greater than or equal to it. The null hypothesis is believed to be true unless there's overwhelming evidence to the contrary. So if we're saying I believe that the mean data use for smartphone users is 1.8 gigabytes per month. That's my null hypothesis. Then our assumption is that's true unless we have some overwhelming data that shows it's not true. Okay? An alternative hypothesis represents the opposite of the null hypothesis. It's believed to be true if the null hypothesis is found to be false. Okay? The purpose of a hypothesis statement is to draw a conclusion about an unknown population parameter. And I think this whole chapter just focuses on either means or proportions, no other parameters in the population. Hypothesis test is often performed to show that a change has occurred from the status quo. So usually it'll be something like this. You know, they've always thought that the average was a certain amount, and now recently, based on observations, somebody says, I think the new average may have gone up. So now that's their hypothesis, right? The statement that it may have gone up. So now you do a test to see, is it in the range of what it used to be, or is it somehow way outside of that range? All right. The alternative hypothesis is used to represent the claim researchers wish to support. Because of this, the alternative hypothesis is also known as the research hypothesis. Okay? So again, H0, the null hypothesis, is the unknown parameter has not changed from the status quo. And the research hypothesis, or the alternative hypothesis, there's been a change in the desired, I don't know if I like the word desired, but in the direction. All right. We'll get through all of this. This is mostly like just terminology. Stating the null and alternative hypotheses depends on the nature of the test and the motivation of the person conducting it. So here, look, this test would be used by someone who thinks the data use has gone up and wants to support that the average data use is now more than 1.8 gigabytes per month. So they have their null, that it is less than or equal to 1.8, and their alternative hypothesis is that it is greater than 1.8. So again, this is someone who says, I think that data usage has gone up. So the null represents the status quo, what it's already been, and the alternative represents what I think may have happened, that it went up. Does that make sense? In this case, this would be used by someone who wants to test an assumption that data has gone down. Rejecting the null hypothesis would support the alternative that the average data use is less than. So here, the null is that it is greater than or equal to 1.8, and the alternative is that it is less than 1.8. And then the last one, the test would be used by someone who has no specific expectation but wants to test the assumption that the average data use is 1.8 gigabytes per month. So our null hypothesis is that it equals 1.8, and our alternative is that it does not equal 1.8. Okay? All right, so there's two different types of hypothesis tests. The first is called a two-tailed hypothesis test. The second is called a one-tailed hypothesis test. All right? A two-tailed hypothesis test is used whenever the alternative hypothesis is expressed as a does not equal. Okay? Why? Because what we're going to say is, if the null hypothesis that it equals 1.8 is true, then we would expect our sample data to fall a certain distance around the mean of 1.8. If it falls further outside of that, then we'll reject the null hypothesis in favor of the alternative hypothesis. So that's a two-tailed test, and it's only used when we're using the equal or not equal for our hypotheses. Okay? The second is a one-tailed hypothesis test, and we use this when our alternative hypothesis is stated as a greater than or a less than. Again, these all the way back to those initial examples. So here it says we have an upper tail test. There's we assume that the mean is 1.8 unless the sample mean is much higher. Okay? And the opposite is what's called a lower tail test. So it depends on what you're testing. Okay? As far as what we want to, whether we're going to accept or reject it. Again, though, if we're testing and we're saying, I think the mean is 1.8, and then we get a sample and the mean of the sample isn't 1.8, does that mean we can automatically reject it? Probably not, because it's within a normal distribution, meaning any sample we get is not going to be perfectly the same as the population. And that's where this idea of confidence intervals that you learned in the last chapter comes into play. So we can say, hey, with 95% certainty, we think that the new mean is outside of the parameters of what the old mean had. Okay. So here's the logic of hypothesis testing. The null hypothesis can never be accepted. The only two options available are to, 1, reject the null hypothesis, or to 2, fail to reject the null hypothesis. In other words, you can never prove that the null hypothesis is correct. You can either disprove it or fail to disprove it. That's it. So hypothesis testing never has a definitive answer. Like, the population mean is 1.8. It doesn't give you that. It says either the evidence shows that there's a chance it could be 1.8 within 95% confidence, or no, it doesn't. Within 95% confidence, it doesn't appear to be that, okay? Let's see. We know that samples are not perfect because of sampling error. So we can have errors, okay? And they break down the error into two different types. And this is one I had to read in the book 10 times when I first learned about this when I was undergraduate, and again when I learned about it as a graduate student and had to take the class again or a class similar to it. I'd like read through these errors, and then again today when I was prepping for this, I was like, oh yeah, type 1 error and type 2 error, still confusing. So type 1 error occurs when the null hypothesis is rejected when it is true. So one error that could happen because our samples are not perfect, okay, is that our null hypothesis, the one that we assume to be true, could be rejected even though it is true. Why? Well, because when you take a sample, it has data from all over the place, and sometimes you're going to have errors. Yeah. Rejected. Well, you came in late, but the whole point of all this is either to, we talked about it briefly, but I don't know that anybody else understood it any better, so it's a good question. Our only answer can be either we accept the null hypothesis or we don't. So there are times when the null hypothesis could really be true, that the mean is, that the mean of the population data really is about 1.8 gigabytes per month is what the example was. And yet, because of sampling error, we could come up with the answer that it's not and reject it and say, no, it must be greater or less than that. So that's called a type 1 error. A type 2 error occurs when we fail to reject the null hypothesis when it's not true. So meaning it really is false, but because of sampling error, we fail to reject it. We fail to recognize that it's not true. And there'll be a little more explanation of that going forward. So the probability of making a type 2 error is known as the beta, okay? And the probability of making the type 1 error is known as the alpha. And we already learned about alpha. That's the level of significance, right? Which was our confidence level, or 1 minus our confidence level. And so what's interesting about this, and I think it'll tell us more later, but they're related to each other. So we always choose the alpha. When we're doing the test, we say, I'm going to do this to a confidence level of this much, that will choose our alpha, which again is our probability of making the error. Okay? And what's interesting is that they're related to each other and that they're conversely related. Meaning if I want to lower the chance of making an alpha or a type 1 error, then that increases the chance of making a type 2 error, and vice versa. And the only way to reduce my chance of making either type of error is to increase my sample size. And they actually do a pretty good, there's a little display where they kind of show that later on. So here's a little summary of the type 1 and type 2 errors done in a little matrix for you. So here's an example they give you. It says, consider manufacturing or quality control setting. Our null hypothesis is that the process is satisfactory, meaning it's doing what it's supposed to do, whatever that is. And our alternative is that it's not. Okay? A type 1 error is known as the producer's risk, meaning when it occurs, the producer is looking for a problem in its process that does not exist. Whereas a type 2 error is known as the consumer's risk. So remember, type 1 is when the null hypothesis is rejected even when it's true. So what we're saying is it occurs when the producer is looking for a problem that does not exist. We've rejected the null even though it really is true. Okay? And a type 2 error occurs when we fail to reject a null hypothesis when it is not true. And they call that the consumer's risk, because that means we're putting out product that was where there was a problem in how it was being manufactured. Correct. In the sense, well, at least from a product liability standpoint, right? In other situations, maybe not. So that's something you have to decide too. Right. Exactly. Or your brakes fail to work on the cars you manufactured or whatever. Okay. And that's how this starts to apply into business. And so, Damien, back to your kind of thinking, a managerial accountant probably doesn't have to know how to do all these calculations, but they need to recognize that processes can have errors and understand that there's a means by which those things are tested for and that there's a relationship between the two. Would there be experts you would bring in if you had some process problems? For sure. They wouldn't put it all on the accountant to the company. But back to the question of why does an accountant even have to learn about this? Because you have to understand the concept, even if you don't remember all the process. All right, so when doing a hypothesis test, decide on a value for alpha before selecting the sample. That's what I just said. Once the alpha has been set, the value of beta can be calculated. Okay, that's all the stuff I just told you, so we'll go from there. All right, so let's get into how we do it. So again, the way they break this down is testing for a population mean, and that's where you either know the population standard deviation or you don't, and then testing for a population proportion. So hypothesis testing when the population standard deviation is known. This is kind of nice. If the sample size is small, less than 30, the population must follow a normal distribution. If the sample size is large, greater than or equal to 30, then the central limit theorem applies, meaning still going to go to a normal distribution. So no matter what, when we're doing this, we use a normal distribution. All right, so here's an example. A new CFL bulb is claimed to have an average life that exceeds 8,000 hours. Suppose the average life of a random sample of 36 new bulbs is 8,120 hours. Assume that the population standard deviation for the life of the CFL bulb is 500 hours. All right, so they're going to walk us through the steps of doing a hypothesis test. The first step is almost always the hardest to me. All right, so step one is identify the hypotheses. All right, so remember that the null hypothesis typically represents the status quo. Okay, so in this case, if we're saying we think that this new bulb exceeds 8,000 hours on its average life. So our null hypothesis is the status quo, which is that the average life is less than or equal to 8,000 hours, or not greater than 8,000 hours. And our alternative or research hypothesis is that the bulb lasts longer than 8,000 hours, or is great, like what we think might be the case. Okay, that's the way they usually set these. Step two, set a value for the significance level, alpha. It's usually given to you in a problem, right? If you were working in a business where you're actually doing some type of testing of product, then the business would decide. So in this case, they want an alpha of 0.5 or a 95% confidence level. Confidence interval, well, not interval, but level. So the level of significance represents the probability of making a type 1 error. All right, determine the appropriate critical value. So since we know the population standard deviation, we'll use a z-score. The critical z-score identifies the rejection region for a one-tailed test. Okay? Since this is a one-tailed test, the entire area for alpha equals 0.05 is placed on the right side or upper tail of the sampling distribution. So if we're doing a 5%, what do they call it? Significance level. That's a 95% confidence level. And because it's a one-tailed test, right, we're testing either greater than or less than, the whole 5% goes on that side. So what we're saying is, if we get a value anywhere in this 95%, then we're not going to reject the null hypothesis. And remember, the null hypothesis was that it was less than or equal to 8,000 hours. If we get something that's above 1.645 standard deviations from the mean, then we think we have enough information to reject the null hypothesis and go with the alternative hypothesis, that we have data that indicates it's likely, 95% confidence, that the new population mean really is above 8,000 hours. Okay, that's the idea behind hypothesis testing. So the z is 1.645. We could find that by looking it up on the z table at 0.95. All right, once we have that, we can calculate the appropriate test statistic. The formula for the z-test statistic for hypothesis test for the population mean when sigma, or when the population standard deviation is known, is right here. There's your formula. Plug in the numbers, calculate it out, gives us 1.44. Now we'll compare the z-test statistic with the critical z-score. If you remember, the critical z-score was 1.645. So in this case, if you remember our hypotheses, the null was that it was less than or equal to, and the alternative was that it was greater than. So in this case, we're not going to reject the null. So what that means is, well, and they'll tell us step 6 then is to state the conclusion. According to the sample of 36 new bulbs, there's not enough evidence to support the claim that the average life of these bulbs exceeds 8,000 hours. Okay? Even though, if you look all the way back at our data, our sample had an average life that exceeded it, right? The average life of the sample was 8,120 hours. But because that standard deviation is 500, we can't prove it. Okay? And that's what's interesting about all of this. Again, it's back to that earlier thing I said, the earlier statement of we can't ever prove that the null hypothesis is true. We can either disprove it or fail to disprove it. But just because we failed to disprove it doesn't mean that it really is false. It means it's highly likely, given this sample, with 95% confidence, that the null hypothesis is true. That they really are still less than 8,000 hours. But we've got a 5% probability that we're wrong on that, right? And that's what the confidence interval is all about. So I know this seems a little complicated, but I promise you the math isn't hard. I mean, it's not any harder. In fact, I think it's easier than a lot of the math we've done already. Okay? All right, another approach to doing this hypothesis testing is what's called finding the p-value. The p-value is the probability of observing a sample mean at least as extreme as the one selected for the hypothesis test, assuming a null hypothesis is true. The p-value is sometimes referred to as the observed level of significance. Remember, we set our significance level. In this case, it was 0.05. And then we could say, well, let's observe where the sample comes in at. Okay, so here's the same example, the CFL bulb example. The claim is that the mean of the population is greater than or equal to 8,000. Sample result n equals 36. Sample mean 8120. Population standard deviation of 500. P-value represents the probability of obtaining a sample mean. So here's how you figure out that probability. Really, it's just the z of the mean, okay? And it comes out to 0.0749. And then it's the exact same thing. So here, we have a p-value of 7.49%. That's the probability that it would be there. But we were looking for a probability of 5% on the alpha. And so since 749 is greater than 5%, you reject it. All this is another approach. What's nice about using this approach is you can calculate the p-value using Excel. Okay? Norm.s.dist it'll calculate it'll actually calculate the complement of the p-value, and then you take 1 minus that to get the p-value. That's what it does. And then you can compare that to the confidence, or not the confidence, I just forgot what it's called, the complement of the confidence level, significance, and that's how you do it. All right, so here's their example. The mean data use for smartphone users is claimed to be 1.8 gigabytes per month. This is a two-tailed hypothesis test now. We just did a one-tail. This is a two-tail. Suppose data use is recorded for 49 randomly selected smartphone users and the average use is found to be 1.86 gigabytes per month. Assume the population standard deviation is 0.2 gigabytes per month. So first thing we do is identify the null and alternative hypotheses. The null is that it equals 1.8, and the alternative is that it does not equal 1.8. We set the significance value. In this one, they're going to choose significance of 0.05. So a confidence level of 95%. Okay. We determine the appropriate critical values. Population standard deviation is known, so we can use a z-score. Since it's a two-tailed test, an alpha of 0.05 is split evenly to two tails, or 0.025 on either side, which gives us a z of 1.96. Okay. In fact, if you next time you go back and look, well, you'll see when you get to the t table, it breaks it down into whether it's one-tailed or two-tailed, so that you can see it. Remember, that was a little bit of a confusing thing about this, about finding the critical z was like if it was 5%, then I had to split it into 2.5% on either side of the thing, and so I have to look up actually 975, even though it's 5%. I don't know if that was confusing to you. It was to me at first when I was trying to figure it out. But it's because on a two-tailed test, you have a 95% area in the center and 2.5% on either side in order to have 95%. I keep forgetting the terms. I'm sorry. In order to have a 95% confidence level. Whereas on a one-tailed test, you had 5% on the one side of it, and then 95% on the other. Okay, and that's why the z-score will change whether you're doing a one-tailed or a two-tailed test, and that's an important thing to wrap your brain around. All right, so we calculate the appropriate test statistic. Again, there's the formula. It's not tough. You crank it out. Then you compare the z-test statistic with the critical z-score. In this case, we came out with 2.1. It's greater than the 1.96 critical z, so we're going to reject the hypothesis. And I like the way they show it on this picture, where you can see it more graphically laid out. Final step is to state the conclusion. All right. P-value approach. It's the same concept, but instead we're just using the p-value. Again, why? Because you can use Excel to calculate the p-value. I think that's the main reason. It's a better approach for us, is we can just plug it in there. We'll get the complement of the p-value, and voila, we can compare it. All right. So the role alpha plays in hypothesis testing. Changing alpha changes the critical z-score in the hypothesis test, which in turn changes the rejection region on the sampling distribution. I think that's shown pretty good in the pictures. And see right here how they show you. So if you have an alpha of 0.01, if it's one-tailed, it's going to be always going to be a lower critical z-score than if it's two-tailed. And again, that's because if it's two-tailed, you have to split that alpha in half and put it on either end. All right. So there's a little chart. All right. So if our population standard deviation is unknown, we've figured out already, if we don't know the population standard deviation, no problem. We're going to assume that it follows a standard distribution, or a normal distribution, and we're going to assume that we can use the sample standard deviation rather than the population standard deviation, but then we can't use the z-score, so instead we'll have to use the t distribution, right, which is similar to a normal distribution, but it's wider, so there's more error involved in it. All right, that's probably everything I just said, so I'll move forward. So they'll give us an example. The average cost of a hotel room in Chicago is claimed to be $188 a night. Travel agent thinks it's lower now. Random sample of 25 hotels resulted in an average of 177.50 and a standard deviation of the sample of 2540. Test the appropriate hypothesis using alpha 0.5. So first we identify the null and alternative hypothesis. Status quo, that the average cost is not less than 188. And our alternative, that the cost now has gone down, in fact, which is what they thought, right? So that's always the pattern, again, that the null hypothesis is what it was before, and the alternative is what you think it probably is now. Okay? We set the value for the significance level, alpha 0.5. We determine the appropriate critical value. Since our population standard deviation is unknown, we use a t-score, where n is 25, so we use 24 degrees of freedom. Since it's a one-tailed test, the entire area for alpha of 0.5 is placed on the left side or lower tail. So we're going to reject it if it falls into this region. We won't reject the null if it falls into that region. The critical t-value can be found in a table, Appendix A, or with Excel's t.inv function. This function returns the left tail critical t-score, so the absolute value of the result for the upper tail test here, okay, 1.711. Then we calculate the appropriate test statistic using that formula. Looks a lot like the Z's test statistic. Comes out with a negative 2.07. We compare it to the t-test statistic, and since it's lower than our critical t, we're going to reject the null hypothesis. I promise you, once you get into these, they're not too bad, okay? Even though, again, I think the hardest thing is all the terminology, right? They're using all this crazy statistics terminology, but none of the math that you saw there was hard math, right? I mean, it's pretty doable. We state the conclusion, voila. We can estimate the p-value using the student's t-distribution. Everything's the same, except now we're using t, so we have to worry about degrees of freedom. We find the p-value. In this case, because it falls between two, we have to make an estimate. You can find the precise p-value by using the t.dist, and then you can test it, okay? So here's a two-tailed hypothesis test where we don't know the population mean, or for the population mean when we don't know the population standard deviation. Again, it's the same stuff. Here's the claim. Average person in the U.S. watches 34.5 hours of television per week. Does anybody in this room watch that much television per week, do you think? I don't. That's a crazy number. Yeah, but I guess it's like, you know, maybe when you're retired and like you don't do anything else. I don't know. My in-laws are retired and I don't think they watch that. That's what, 7 hours a day? Or that's 5 hours a day? That's crazy. All right, suppose viewing data is recorded for 10 people and the sample mean is found to be 39.6 hours and the sample standard deviation is 16.4 hours per week. The following slides show the steps. All right. Identify the null and alternative hypothesis. So the status quo would be that the average time is 34.5. And the alternative would be that it is not 34.5. We set the significance level for this one. They want to do 0.02. We determine the appropriate critical values. Since the population standard deviation is unknown, then we have to use a t-score where our alpha is 0.02 and our degrees of freedom is 9. Okay? Since it's 0.02, then we're going to do 1% on this side, 1% on that side. Yeah.
Do you think that counts the people that just kind of have the TV on?
I think it must.
Yeah, because I looked it up and said the average person watches 5 hours of TV a day in America.
Uh-huh.
I couldn't see someone sitting. I'm sure there
But they only can measure that through like Nielsen boxes and stuff, and those can't tell whether or not you're sitting there watching, right? They just tell whether the TV's on. So good point. Anyway, So again, we find our critical t value either in the appendix or using Excel's t.inv.2t function. Once we have our critical t, we calculate our test statistic. We compare our test statistic to our critical t. And in this case, the test statistic falls very squarely in here, so we're not going to reject the null hypothesis. Again, when we say we're not rejecting the null hypothesis, all we're saying is that given this 98% confidence level, we don't have, the data here is not showing that it's likely that the sample data falls outside of what the status quo has been. Okay, that's all that means. I think that's the hardest part about this, is kind of interpreting it and meaning, what does that mean? So our random sample of 10 viewers does not provide sufficient evidence to reject the null hypothesis. So we have no evidence to conclude that the average does not equal 34.5%. Did that prove that the average does equal 34.5? No. We just are saying that sample doesn't indicate that, or doesn't give us enough proof that it doesn't equal that. All right, and hypothesis testing for a proportion. Have you noticed now the last couple chapters, it's been when you know the population standard deviation, when you don't know it, and then for a proportion. When you know it, you use a z-score. When you don't know it, you use a t. And for the proportion, it follows a similar pattern as well. So proportion data followed by binomial distribution, which can be approximated by the normal distribution if the sample size times the probability is greater than or equal to 5, and if the n times 1 minus the probability is greater than or equal to 5. That's been the same in every chapter. Okay. The formula for the proportion has been the same in every chapter we've looked at proportions, the number of observations divided by the sample size. The formula for the z-test statistic for the hypothesis test for the proportion, that's something that's new that we haven't had in previous chapters. But again, you take the sample proportion minus the population proportion, which is assumed to be true in the null hypothesis. Divide that by the square root of population proportion, which is assumed to be true, minus 1 minus it, divided by n, which actually, if you think about it, is very similar to the ones we were using in the last chapter. They're related. Again, I'm not a mathematician. You know, I'm not the guy that sat around and came up with how this all works. And so, like most other people, I have to know enough of it to use it, but not enough of it to understand the whole theory behind how it was achieved. If I worked with it more and like stay in my day-to-day life, might I start to gain insights into how it's all interconnected? I probably would, right? Like in accounting, you know, I understand how a lot of things are interconnected with each other there because I use it all the time. Here's their example. The proportion of cell phone users with 4G contracts last year was 62%. Verizon executive thinks the proportion has increased this year. So they want to test that. Suppose a random sample of 350 users, 238 have 4G contracts, test at an alpha of 5%. So we identify the null and alternative hypotheses. Again, the null is the status quo, that P is not greater than 62%. And the alternative is that the proportion has increased. So this is going to be a single-tailed test, right? We set the value at alpha is 5%. We determine the appropriate critical value. Binomial distribution can be used to approximate, can be approximated with the normal distribution. So we use a z-score for alpha is 5%, and the z-score is going to be 1.645, right? If it were two-tailed with an alpha of 5%, it would be 1.96. Already starting to memorize a few of those that we used a lot. But single-tailed, it's because we have 95% on this side and a full 5% on the right. Since it's a one-tailed test, the entire area, okay, that's what I just said. All right, calculate the appropriate test statistic. Find the sample proportion and the z-test statistic for the hypothesis test. So first we find the proportion by taking the number of observations, 238 divided by the number in the sample of 350, it gives us 68%. Then we plug it in, work it out, and we come up with a z-test statistic of 2.31. Since that 2.31 is greater than the 1.645, we're going to reject the null hypothesis. It doesn't seem very likely that taking a sample of that size and getting that mean, which is 2.31 standard deviations above the mean, right? It doesn't seem likely that that the null hypothesis is true anymore. It must be higher than that than our null hypothesis. As you think about it, that's just quite a ways to the right. Then we state it, we can conclude at a 5% level of significance that the proportion of people with a 4G contract has increased above 62%. P-value approach, same idea. There's our rejection region, alpha of 5%. Our p-value, since the p-value is a 0.0104%, or that means what, 1% chance that the mean is going to, 1% chance that we would find a mean there. And we're just testing at the 5% level. We're going to conclude that that's the case, that we reject the null and go with it. We can use the norm.s.dist function to determine the p-value for this example. And again, when you do that function, it's going to return, it always returns to the left of whatever you're testing, right? So you're going to have to take 1 minus what you get from the function. All right, so one thing we haven't talked about are type 2 errors very much. So we said the probability of a type 2 error is known as the beta. And the beta is the probability of failing to reject a false null hypothesis. Once we set the value for alpha, the value for beta becomes fixed. That's what I already mentioned. The two are inversely related, and the only way to lower the probability of both errors at the same time is to increase the sample size. To calculate beta, we assume the null hypothesis is not true and should be rightfully rejected. The value of beta depends on the actual value of the population mean. That is true if the null hypothesis is false. This is confusing, so don't worry too much about it. Even though we don't know the population mean, we can specify a value for the population mean and calculate the corresponding values of B. Like I said, I think that was confusing. It'd be something you have to think about a lot, and even then you'd still be confused a little bit by it. What I'm telling you is don't worry too much about this concept. What's most important is that you understand is what a type 1 level error or a type 1 error is and what a type 2 error is, the difference between the two. You recognize that they're inversely related, meaning as I lower that alpha, the chance that my beta is going to get bigger. And as I increase the alpha, because I set the alpha, I choose that when I'm doing the calculation. As I increase it, then the beta will get lower. And that there's only one way to really lower both of them, and that's just to increase sample size. Those are the things that really matter. Okay?